For celestial bodies, such as massive stars and planets, gravitational forces are decisive. Einstein's general theory of relativity considers gravity as the curvature of space under the influence of mass. The gravitational behavior of galaxies clearly indicates the presence of an invisible mass called dark matter. Immense gravity allows strong nuclear forces to ignite powerful thermonuclear fusion in the cores of stars.
Welcome. Today we are going to conduct a detailed analysis of gravity. You know, it's a force so astonishingly weak at the atomic level that it's almost undetectable. Yet it is powerful enough to forge stars, sculpt entire galaxies, and dictate the ultimate fate of the universe. So how can this be? How can the feeblest force we know of simultaneously be the master architect of the cosmos? Well, that's what we're here to explore.
Okay, so to really get a handle on gravity's power, we need to contrast it with another fundamental force, electromagnetism. You see, electromagnetism acts on positive and negative charges, which, over large scales, tend to cancel each other out, neutralizing the force. But gravity, it's a completely different beast. It only acts on mass, and here's the kicker. Mass only adds up. There's no such thing as negative mass to cancel it out. Every particle adds its own little bit of pull, and that relentless, cumulative attraction is the secret to its cosmic dominance.
So here's our roadmap for this analysis. We'll begin with the dominant nature of gravity, then move to Newton's classical view, what I like to call the Newtonian architecture. From there, we'll jump to Einstein's radical reconceptualization of curved spacetime, and then we'll look at how we're now listening to the universe. We'll end up right at the frontier of modern cosmology, staring into the dark mysteries of the cosmic web and placing gravity within the context of all four fundamental forces. Right. So it's precisely this relentless, one-way accumulation of mass that makes gravity the ultimate cosmic player. Now, let's formally begin our examination with the first blueprint for this cosmic architecture, the one designed by Sir Isaac Newton. And that brings us to the Newtonian architecture. You know, Sir Isaac Newton's laws of universal gravitation, they gave us the first coherent rulebook for the cosmos. And in doing so, they revealed four fundamental roles that gravity plays in shaping everything we see.
And these roles are truly profound. First, motion. Newtonian gravity dictates the orbits of everything, from planets around stars to stars around galactic centers. Second, shape. It's gravity that imposes that beautiful sphericity on any large celestial body. Third, internal structure. It governs the immense pressures and temperatures deep inside stars. And finally, evolution. It's the compressive force of gravity that kickstarts thermonuclear fusion, literally igniting stars into existence.
This leads us to a crucial concept, hydrostatic equilibrium. I want you to picture a star as the site of a constant, titanic struggle. On one side, you have the relentless inward crush of gravity, trying to collapse the star into an infinitesimally small point. And fighting against it is the incredible outward push of thermal and radiation pressure from the nuclear furnace in the core. The entire stable life of a star, we're talking millions, even billions of years, is spent in this perfect, violent balance.
Now, as powerful and predictive as Newton's framework is, it is ultimately an approximation. It works beautifully for our solar system, but it begins to break down at cosmic extremes. Think near a black hole, or at the very beginning of the universe. To understand those phenomena, we need a complete revolution in our thinking, and that revolution was delivered by Albert Einstein.
For centuries, this was it. This was our understanding of gravity, an invisible force acting instantaneously across the vastness of space. It's elegant, it's powerful, it makes incredible predictions, but it left a huge question unanswered. It told us what gravity does, but it gave us absolutely no clue as to what gravity is.
And this is Einstein's genius. He proposed that gravity isn't a force in the traditional sense at all. Instead, gravity is the curvature of space-time itself. The classic analogy is a trampoline. If you place a heavy bowling ball in the center, it creates a deep curve in the fabric. Now, if you roll a marble nearby, it isn't pulled by the bowling ball. No, it's simply following the curve in the trampoline fabric created by the bowling ball. In this analogy, the sun is the bowling ball, space-time is the trampoline, and the Earth, well, the Earth is just the marble, following the curve.
I mean, what an absolutely incredible idea. And for a long time, it was primarily a theoretical one. But in just the last decade, we have finally developed the technology to directly observe its consequences, to quite literally listen to the vibrations of space-time itself.
And this really highlights the incredible arc of scientific discovery. Think about it. In 1916, Einstein predicts these ripples in space-time, which he called gravitational waves. They were just a mathematical consequence of his theory. A full century passes. Then, in 2015, the LIGO Observatory makes the first direct detection of these waves. We heard the sound of two black holes merging a billion light-years away. And then, just a few years later, in 2019, the Event Horizon Telescope gave us the first direct image of a black hole shadow, a dark silhouette against a ring of light, with space-time bent around it exactly as Einstein's equations said it would be. So, Einstein's theory of general relativity has proven to be so incredibly accurate that we've now flipped the script. We use it as a tool. By precisely measuring the gravitational effects on the matter we can see, we can infer the presence of matter and energy that we cannot. And when we do this, well, the results are nothing short of staggering.
You see, when we use gravity to perform a cosmic census, to tally up all the mass and energy in the universe, we come to an incredibly humbling realization. Everything we've ever observed directly, every star, every galaxy, every planet, all of it amounts to only about 5% of the total cosmic inventory. The other 95% is composed of two completely mysterious components we call dark matter and dark energy.
So let's start with the first mystery. What is dark matter? Well, we know it must exist because galaxies are spinning far too quickly. Based on the stars and gas we can see, they should have flown apart billions of years ago. The visible matter just doesn't provide enough gravitational glue. There must be some other source of gravity, a vast, invisible halo of mass holding it all together. We can map its gravitational effects with precision, but what it's actually made of, that remains one of the single greatest unsolved problems in all of physics.
And the second mystery is, if anything, even more profound. For most of the 20th century, cosmologists debated whether the universe's expansion would slow down and eventually reverse, or slow down forever. But observations in the late 90s revealed something shocking. Neither is happening. The expansion of the universe is accelerating. Some unknown, repulsive influence is pushing space-time itself apart. We've given this a name: dark energy. It makes up the majority of the universe, and we have almost no idea what it is.
Okay, so we've established gravity's absolute dominance on the cosmic scale. But to fully appreciate its unique role, we have to place it in its proper context, alongside the other three fundamental forces of nature.
This table gives us a nice summary. The way I like to think about it is this. Gravity is the grand architect and the general contractor. It gathers all the raw materials and assembles the structures, stars, galaxies. But it's the other three forces that actually make things happen inside those structures. The strong nuclear force is what enables fusion in a star's core. The weak nuclear force governs key particle transformations in that process. And the electromagnetic force is what carries the energy produced, the starlight, out across the cosmos. They are all essential.
And this brings us full circle to the central paradox of gravity. At the scale of fundamental particles, gravity is almost comically weak. Compared to the electromagnetic force between two protons, for instance, it is weaker by this staggering factor. A 1 followed by 36 zeros. It is almost incomprehensibly feeble.
So here's the resolution to the paradox. Gravity's role is not to be the strongest, but to be the most persistent. It overcomes its profound intrinsic weakness simply because it is cumulative and it has the entire universe to work with. It is the great gatherer. Its job is to assemble the stage, to collect immense quantities of matter and compress it, creating the extreme conditions, the pressure cooker core of a star, where the far more powerful but short-ranged nuclear forces can finally take over and perform.
And so we are left with this final profound question. How can the universe's feeblest force simultaneously be its master architect? A force that is utterly negligible at the scale of an atom somehow dictates the grand structure of galaxies, the life and death of stars, and the ultimate destiny of the cosmos itself. Reconciling this incredible duality remains one of the deepest and most compelling pursuits in all of science.
Thank you, friends. Strive for understanding and become wiser. See you soon.